Here's our next example. Consider the series n goes from 1 to infinity of a pretty complicated looking general term. I'm going to do -1 to the n power times n factorial times n plus 1 factorial, all divided by 2n quantity factorial. Yikes. Does this converge or not? Now, once again, when you're not told what to do, the first thing you do typically want to do is think about, do the terms go to 0 or not? It's not so clear here. Both the numerator and the denominator, if I sort of ignore the -1 to the n power, are getting large very rapidly as n gets large, right? If n is 10, for example, 10 factorial is over 1 million already. And this would be 11 factorial, which would be over 10 million. 1 million times 10 million is what? 10 trillion? The numerator is over 10 trillion when n is already just 10. What about the bottom when n is 10? It would be 20 factorial. 20 factorial is in the quintillions or hextillions or something like that. I don't know. I'm not going to, I could use my calculator, but yeah, 10 to the 20th, 10 to the 30th, somewhere in that kind of ballpark. Humongous as well. Though the ratio, 10 to the 10th divided by 10 to the 20th is technically small. The ratio is small. If we wanted more confirmation, we could type the nth term into Mathematica like this and say, Mathematica, for example, what is A10? It's 1 over 16,796. Now, what is 20 factorial anyway? That. Million, billion, trillion, quadrillion, 2 quintillion, 2.4 quintillion. By the time we hit the 10th term, we are at a fairly small number. Let's try the 20th term. Really, really small. Intuitively, it should seem, therefore, that probably the series, the infinite sum, converges because the terms are going to 0 seemingly pretty rapidly. That's not clear from just looking there, though, right? If you want extra proof, let's use the ratio test. So this is now my an. That's my nth term that's being added. I'm not going to bother writing it out with the plus ... dots here. What is the ratio of the absolute value of an plus 1 to the absolute value of an? Here, I really do need the absolute value signs because I have those -1s in there. Though, because I am using absolute value signs, those -1s to those powers will go away. Notice what's happening here. In the numerator, I am replacing, up here, I am replacing in this expression each n with n plus 1. That is the absolute value of an plus 1. Divide by the absolute value of an. And we get this crazy looking thing. Looks insanely complicated. It's not as bad as it looks. We can get rid of the absolute value signs and get rid of the -1s to those powers at the exact same time. Think about it. If you're raising -1 to an odd or even power, you either get plus or -1, and its absolute value is always +1. You can get rid of those things. And with what's left without those -1s, those quantities are always positive. So in the end, we can get rid of the absolute value signs. And we're left with this. Let me also simplify there by multiplying the 2 through. I'm dividing by another fraction, so I multiply times its reciprocal. Like this. All right. What's the limit of that as n goes to infinity? You can do some cancellation. You can actually cancel the n plus 1 factorials right away. Also, that thing right there is the same as n plus 2 times n plus 1 times n minus 1 times n minus 2, etc. In other words, times n factorial. And so that n factorial right there will cancel with this n factorial right there. Likewise, you can do something similar with this. That's the same as 2n plus 2 times subtract 1, 2n plus 1 times subtract 1, 2n times 2n minus 1 times 2n minus 2. In other words, times 2n factorial. And this will cancel with this. Is there anything that didn't cancel? Yeah. The n plus 2 times n plus 1 up top, and the 2n plus 2 times 2n plus 1 on the bottom. And while we could use the FOIL method to expand this, there's really no need to. It's a rational function of n. The degree of the top and the bottom are both 2, the same. It's going to approach a ratio that's the ratio of the leading coefficients, 1 and 4. 1 from n times n gives you 1n squared. 4 from 2n times 2n, 4n squared. This approaches 1/4 as n goes to infinity, and that is less than 1. Therefore, the series of the ANs, which is kind of complicated series again. This complicated series, I'll rewrite it for emphasis. This does converge. This converges by the ratio test. Okay? It can be done. Pretty much anytime you have a problem with factorials in it, you're going to want to use the ratio test. Oftentimes, if you have an exponential function of n, the ratio test is also useful.